November 3, 1944. Grumman Aircraft Engineering Corporation, Bethpage, Long Island. The twin Pratt and Whitney engines roared to life as test pilot Corwin Meyer settled into the cockpit of what would become aviation's most lethal secret. His gloved hand rested on the throttle of aircraft designation F7F, a machine so advanced that its very existence challenged everything the aviation world understood about fighter aircraft capabilities. The instrument panel glowed with readings that made Meyer's pulse quicken. Airspeed indicator calibrated to 460 miles per hour. Rate of climb gauge marked to 4,500 feet per minute. For 20mm cannons and 450 caliber machine guns, more firepower than an entire flight of conventional fighters combined. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow, I've saved something extra special for you. As Meyer pushed the throttles forward and felt 2,400 horsepower surge through the airframe, he understood with absolute certainty that he was piloting a weapon that would have turned the Pacific Air War into a massacre. The Japanese Mitsubishi A6M Zero, the aircraft that had terrorized Allied pilots since Pearl Harbor, would have been defenseless prey against this twin-engine predator. Every advantage the Zero possessed, agility, rate of climb, operational range, would have meant nothing against the Tigercat's overwhelming speed and devastating armament. But Meyer also knew something that filled him with a strange mixture of relief and regret. By the time this aircraft reached operational squadrons, the war would likely be over. The Japanese would never face this killing machine in combat. They would never know how close they had come to encountering an aircraft that would have swept their finest pilots from the sky like leaves before a hurricane. In the engineering offices overlooking the runway, lead designer William Schwendler watched through binoculars as Meyer executed a vertical climb that defied physics. The Tigercat clawed skyward at an angle no single-engine fighter could match, its twin tails gleaming in the autumn sunlight. Schwendler had spent 3 years developing this aircraft, pouring every lesson learned from Pacific combat reports into its design. He had studied gun camera footage showing Zeros dancing around American fighters. He had read after-action reports describing how Japanese pilots exploited their aircraft's superior maneuverability to survive encounters they should have lost. He had interviewed dozens of naval aviators who returned from the Pacific with tales of an enemy aircraft that could outclimb, outturn, and outrange anything America could field in the war's early years. The Tigercat was Schwendler's answer to every one of those advantages. It was faster than any Japanese fighter by more than 100 miles per hour. It climbed faster than aircraft half its weight. It carried enough ammunition to engage multiple targets without concern for conservation. It possessed radar for night operations, something Japanese fighters completely lacked. Most crucially, it was built like a fortress while the Zero was constructed like origami, trading structural integrity for weight savings that American engineers considered suicidal. Schwendler's assistant, a young aeronautical engineer named Patricia Donnelly, stood beside him making notes on a clipboard. She had joined Grumman fresh from MIT in 1942, one of the few women working in aircraft design during the war years. Her calculations had solved the wing loading problem that initially plagued the Tigercat's development, enabling the aircraft to maintain maneuverability despite its size and weight. She watched Meyer execute a series of combat maneuvers that would have torn the wings off lesser aircraft. The Tigercat rolled, dove, climbed, and turned with a grace that seemed impossible for something weighing over 15,000 pounds fully loaded. Donnelly had spent months analyzing Japanese aircraft performance data obtained from captured Zeros. She knew their strengths and limitations better than most combat pilots. She understood that the Zero's legendary agility came at a terrible price, an airframe so lightly built that a single burst of .50 caliber fire could tear it apart. American pilots called them flying cigarette lighters because they ignited so easily when hit. The Tigercat, by contrast, featured self-sealing fuel tanks, armor plating protecting the pilot, and a structure robust enough to absorb tremendous battle damage and return home. The contrast was staggering. A Zero weighed roughly 5,000 pounds empty. The Tigercat weighed over 10,000 pounds without fuel or ammunition. Yet the American aircraft was faster, climbed better, and hit infinitely harder. It was as if Grumman had taken everything that made the Zero dangerous and rendered it obsolete through sheer engineering superiority. The story of how the F7F Tigercat came to exist begins not in engineering offices or wind tunnels, but in the blood-soaked skies over the Pacific where American pilots learned harsh lessons about Japanese aviation capabilities. On December 7, 1941, when Zeros roared over Pearl Harbor providing escort for the attacking bombers, American military aviation received a shocking education. The Japanese possessed a fighter aircraft superior to anything in the American inventory. The Mitsubishi A6M Zero could outmaneuver the Curtiss P-40 Warhawk. It could outclimb the Brewster F2A Buffalo. It possessed greater operational range than any American fighter, enabling it to escort bombers on missions American planners considered impossible. Lieutenant Commander John Thatch, who would later develop the defensive weave tactic that helped American pilots survive Zero encounters, flew combat air patrol over Hawaii that morning. He watched in frustrated disbelief as Japanese fighters danced around American aircraft like matadors around bulls. Every advantage American pilots expected from their training, rugged construction, heavy armament, pilot armor, became liabilities against an enemy that had sacrificed protection for performance. Thatch survived that morning, but many of his fellow pilots did not. In the months that followed, as he interviewed survivors and studied combat reports, a picture emerged of an enemy aircraft that dominated through agility and range while accepting vulnerabilities that American doctrine considered unacceptable. The Zero's design philosophy reflected Japanese naval aviation's unique requirements and cultural attitudes toward pilot safety. Chief designer Jiro Horikoshi had been tasked with creating a carrier-based fighter with unprecedented range and maneuverability. To achieve these goals, he eliminated everything considered non-essential. No armor plating for the pilot. No self-sealing fuel tanks. No redundant control systems. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel, it means a lot to us. Now back to the story. The airframe was constructed from the lightest materials available, with structural members designed to minimum strength requirements. The result was an aircraft that could fly over 1,000 miles, climb to 20,000 feet in 7 minutes, and turn inside any opponent. It was also an aircraft that killed its pilots with terrifying efficiency when struck by enemy fire. American intelligence officers studying captured Zeros in 1942 were astonished by the design choices. Captain Eric Brown, a British test pilot who evaluated a captured Zero, reported that the aircraft's lightness was achieved through construction techniques that bordered on reckless. The skin was so thin that maintenance crews could dent it with their thumbs. Control surfaces lacked the redundancy American designers considered mandatory. The fuel system was a disaster waiting to happen, with tanks that would rupture and ignite from even minor damage. Yet for all its fragility, the Zero was lethally effective in the hands of skilled pilots. Japanese naval aviators entered the war with extensive combat experience from China. They had refined tactics that exploited their aircraft's strengths while minimizing its weaknesses. They fought in coordinated sections, using superior altitude performance and range to dictate engagement terms. Against inexperienced American pilots flying inferior aircraft, they were devastating. The wake-up call sent American aircraft manufacturers scrambling. Grumman, already building the F4F Wildcat for the Navy, immediately began developing improved designs. The F6F Hellcat, introduced in 1943, was specifically engineered to counter the Zero's advantages. It was faster, could dive faster, and featured the rugged construction and heavy armament that were Grumman hallmarks. The Hellcat proved successful, but it was fundamentally a defensive response, an aircraft designed to survive encounters with Zeros rather than dominate them. William Schwendler envisioned something more ambitious. He had been working on twin-engine fighter concepts since 1938, exploring whether multiple engines could provide performance advantages over single-engine designs. The early concepts were promising but flawed, too heavy and complex for carrier operations. Then came Pearl Harbor and the Zero crisis, and suddenly Schwendler's twin-engine fighter program received urgent priority and unlimited resources. The concept was radical. Every successful carrier fighter had been single-engine. Twin-engine aircraft were considered too large and complex for carrier operations, requiring too much deck space and maintenance. But Schwendler saw advantages that outweighed these concerns. Two engines meant redundancy and safety. Twin engines could generate power impossible with single-engine designs. Multiple engines enabled greater weapons load and fuel capacity. Most importantly, twin engines could deliver speed that would neutralize the Zero's agility advantage. The initial design work began in late 1941 under designation F7F. Grumman assembled a team of their most talented engineers, many recruited from the Hellcat program. They worked with unprecedented urgency, knowing that American pilots were dying in the Pacific while Japanese aircraft dominated the skies. Patricia Donnelly joined the team in spring 1942, assigned to solve the wing design problems that plagued early prototypes. The challenge was achieving sufficient lift for carrier operations while maintaining structural integrity for high-speed flight. Her solution involved an innovative wing planform with carefully calculated taper and dihedral that provided both lift and strength. The engineering challenges were immense. Twin engines met complex fuel systems requiring precise balance. The aircraft needed to fly safely on a single engine, crucial for carrier operations where engine failure over water meant certain death. The tricycle landing gear, necessary for forward visibility during carrier approaches, was still relatively new technology. The tail design required extensive wind tunnel testing to ensure stability with asymmetric thrust. By early 1943, the design had matured into something extraordinary. The F7F would feature two Pratt and Whitney R2800 double Wasp engines, the same powerplant used in the Hellcat and Corsair. But where those aircraft used single engines producing 2,000 horsepower, the Tigercat would have two, generating a combined 4,800 horsepower in military power settings. This massive power enabled performance that seemed impossible for a carrier aircraft. Projected top speed exceeded 430 miles per hour. Rate of climb approached 4,000 feet per minute. Combat radius would exceed 1,000 miles with external fuel tanks. The armament was devastating. For M2 Browning 50 caliber machine guns mounted in the wing roots, positioned for optimal convergence. For M2 20mm cannons in the lower fuselage, providing incredible destructive power. Total ammunition load exceeded 2,000 rounds of 50 caliber and 800 rounds of 20mm. The Tigercat could engage multiple targets in a single sortie, something unthinkable for fighters with limited ammunition capacity. Perhaps most revolutionary was the radar installation. The F7F-3N night fighter variant would carry in/APS-6 radar in a pod mounted on the starboard wing. This gave the Tigercat all-weather capability that Japanese fighters completely lacked. While Zeros were grounded by darkness or weather, Tigercats could hunt at night, using radar to locate enemy aircraft that had no idea they were being stalked. The contrast with Zero capabilities was stark. The A6M featured two 20mm cannons and two 7.7mm machine guns, respectable armament but far less than the Tigercat's 8 guns. Zero ammunition capacity was limited, forcing pilots to conserve rounds carefully. Japanese fighters had no radar, no all-weather capability, no redundant systems. They were day fighters dependent on visual acquisition, helpless in conditions that wouldn't slow a radar-equipped Tigercat. Construction of the first prototype began in early 1943 at Grumman's Bethpage facility. The company had expanded dramatically since Pearl Harbor, with employment growing from less than 7,000 workers in 1941 to over 25,000 by 1943. Many were women, recruited to replace men serving in combat. They assembled the Tigercat with the same precision that made Grumman Aircraft legendary for durability. Every rivet was inspected. Every system was tested multiple times. The company's reputation depended on building aircraft that brought pilots home alive. Corwin Meyer, Grumman's chief test pilot, had flown every fighter the company produced. He had pushed Wildcats to their limits and run out early Hellcats, providing feedback that shaped their final configurations. When he first saw the Tigercat mock-up in summer 1943, he understood immediately that this aircraft represented a quantum leap. The size alone was intimidating. With a wingspan of 51 feet and length of 45 feet, it dwarfed single-engine fighters. The twin tails gave it a distinctive profile unlike any carrier aircraft in service. The first flight occurred on November 3, 1944, the moment captured in our opening. Meyer took the prototype through its paces methodically, testing handling characteristics at various speeds and configurations. The initial reports were extraordinary. The Tigercat handled like a much smaller aircraft despite its size. Control response was crisp and immediate. The visibility from the cockpit was excellent, the high-mounted wing providing unobstructed views. Most impressively, the performance exceeded projections. Maximum speed hit 435 miles per hour in level flight, faster than any Japanese fighter by over 100 miles per hour. Rate of climb exceeded 4,000 feet per minute, matching or beating aircraft half the Tigercat's weight. Patricia Donnelly watched from the ground as Meyer pushed the aircraft through increasingly aggressive maneuvers. Her calculations had predicted this performance, but seeing it demonstrated was validation of months of theoretical work. The wing design handled high-speed flight without flutter or control problems. The structure absorbed G-forces that would have destroyed lighter aircraft. Every system functioned as designed. But even as Meyer landed and reported enthusiastic approval, reality was setting in. By November 1944, the Pacific War had turned decisively in America's favor. The Hellcat had achieved air superiority through massive numerical advantage and superior tactics. The Corsair was proving devastatingly effective in Marine Corps hands. The Zero was no longer the threat it had been in 1942. Japanese pilot quality had declined catastrophically as experienced aviators were killed faster than replacements could be trained. The Japanese aviation industry was collapsing under strategic bombing and resource shortages. The Tigercat was a weapon designed to counter a threat that no longer existed in its original form. The brilliant Zero pilots who had terrorized the Pacific in 1942 were mostly dead, replaced by teenagers with minimal training flying worn-out aircraft. American numerical superiority was so overwhelming that even obsolete American fighters could achieve victory through sheer numbers. The sophisticated capabilities built into the Tigercat, the speed, the firepower, the radar, the redundancy, were solving problems the Pacific War no longer presented. William Schwendler understood this bitter irony. He had created the ultimate Zero killer just as the Zero ceased being a threat worth such extraordinary effort. The aircraft he had designed to save American pilots' lives would arrive too late to fulfill that purpose. Production would continue, over 360 Tigercats would eventually be built, but they would see only limited combat at war's end. The decisive battles where the Tigercat could have changed history had already been fought with inferior aircraft and higher casualties. In Japan, Zero pilots who would survive the war had no knowledge that such an aircraft existed. They continued flying their increasingly obsolete fighters, unaware that American engineers had created a machine that would have rendered their tactics suicidal. The information blackout was complete. No Japanese intelligence report mentioned the F7F. No combat encounter provided warning. Japan would surrender never knowing how close they had come to facing an aircraft that would have turned their most skilled pilots into helpless prey. The engineering achievement represented by the Tigercat would influence aviation design for decades, but its immediate impact was minimal. The aircraft that would have massacred Zeros in 1942 arrived in 1945 when it was no longer needed. Japan was indeed lucky, though they would never know it, that the F7F Tigercat never met the Zero in the desperate battles of 1942 and 1943 when the outcome was still in doubt and American pilots were learning bitter lessons about Japanese aircraft capabilities. The transformation of Japanese naval aviation from dominance to desperation unfolded with a speed that shocked even American intelligence analysts. In the spring of 1942, when the Tigercat was still blueprints and mathematical calculations, Japanese carrier pilots represented the most experienced naval aviation force on Earth. Commander Minoru Genda, who had planned the Pearl Harbor airstrike, commanded aviators who had logged thousands of flight hours and years of combat experience over China. These men flew their Zeros with an expertise that turned technical advantages into overwhelming tactical superiority. They understood their aircraft's capabilities and limitations intimately, exploiting every advantage while minimizing vulnerabilities through superb situational awareness and coordinated tactics. Lieutenant Saburo Sakai, who would become Japan's most famous surviving ace, embodied this elite generation. He had entered naval aviation in 1937 and accumulated over 3,000 flight hours before Pearl Harbor. His skill in the Zero was legendary among both Japanese and Allied pilots. In his memoir, Sakai described the Zero as an extension of his own body, responding to the slightest input with precision that made aerobatic maneuvers feel natural. He could sustain turns that would black out less experienced pilots, maintain perfect situational awareness during chaotic dogfights, and make snap judgments that kept him alive through hundreds of combat missions. American pilots who faced these elite Zero pilots in early 1942 described encounters that felt less like combat and more like being hunted by predators who could anticipate every move. The Japanese would appear from advantageous positions, strike with devastating accuracy, and disengage before American fighters could respond. Their formation discipline was impeccable. Their marksmanship was exceptional. Their confidence bordered on arrogance because it was justified by consistent victory. But this elite force contained fatal structural weaknesses that would doom Japanese naval aviation regardless of aircraft quality. The training pipeline that produced pilots like Sakai required years of intensive instruction and thousands of flight hours. Japan lacked the fuel, aircraft, and instructor capacity to rapidly expand this system when war came. Worse, Japanese doctrine treated pilots as irreplaceable assets but provided inadequate measures to preserve them. No rotation system existed to pull experienced aviators from combat for instructor duties. No emphasis on pilot rescue meant that aviators who ditched at sea were often lost even if uninjured. Most catastrophically, the decision to equip Zeros with minimal protection guaranteed that even minor battle damage would kill pilots who could have survived in more robust aircraft. The mathematics were brutal and inevitable. Japan began the Pacific War with roughly 3,500 trained naval aviators. American industrial capacity and training infrastructure could produce that many replacement pilots every few months. By mid-1942, the Imperial Japanese Navy was losing experienced aviators faster than the training system could replace them. Each carrier battle killed not just aircraft but irreplaceable human expertise. At Coral Sea in May 1942, Japan lost experienced pilots and 2 carriers damaged. At Midway in June, the disaster was even worse. 4 fleet carriers sunk, over 300 aircraft destroyed, and more critically, over 100 of Japan's most skilled aviators killed. The Midway losses would have been recoverable if Japan possessed American-style training capacity. The carriers could be replaced, the aircraft rebuilt. But the pilots could not. The men who died at Midway represented thousands of hours of training and years of combat experience. Their replacements would be teenagers with barely 200 hours of flight time, thrust into combat against American pilots who now possessed their own accumulating experience and increasingly superior aircraft. Commander Tadashi Nakajima watched this deterioration from his position overseeing training at Chuchiura Air Group. In peacetime, his training program took 3 years to produce carrier-qualified pilots. By late 1942, he was being pressured to graduate students in 6 months. The quality decline was catastrophic and obvious. Student pilots who should have washed out were being passed to meet desperate demand for replacements. Basic flying skills that were once prerequisites for carrier qualification became optional. Advanced tactics that required hundreds of training hours were abandoned entirely. Nakajima submitted repeated reports warning that the accelerated training was producing pilots who would die on their first missions. His warnings were ignored. The operational commands needed bodies in cockpits. Whether those pilots survived long enough to become effective was secondary to having someone available to fly the aircraft. The brutal calculus of attrition warfare meant that even poorly trained pilots served a purpose, forcing Americans to expend ammunition and time dealing with them. By early 1943, the decline in pilot quality had become so severe that experienced American aviators noticed immediately. Lieutenant Alex Fraissiou, flying Hellcats from USS Intrepid, encountered Japanese formations that he described as shockingly incompetent compared to earlier in the war. Enemy pilots flew predictable patterns, showed poor situational awareness, and made elementary tactical errors. Fraissiou shot down 6 aircraft in one mission not through exceptional skill but because his opponents made mistakes no trained pilot should commit. The Zero itself remained a capable aircraft in skilled hands, but increasingly those skilled hands were dead or assigned to training duties. The teenagers flying Zeros in 1943 and 1944 lacked the experience to exploit their aircraft's advantages. They couldn't sustain the high G turns that made the Zero legendary. They couldn't maintain formation discipline during combat. They couldn't make the split-second decisions that kept pilots alive. They were lambs sent to slaughter an aircraft that required expert handling to be effective. This was the context into which the Tigercat would have arrived if production had begun 2 years earlier. Instead of facing elite pilots who could have at least attempted to counter its advantages through superior tactics, the F7F would have been unleashed against the experienced Japanese aviators of 1942. The result would have been massacre on a scale difficult to comprehend. Consider the fundamental matchup. A Zero flown by even an expert pilot had a maximum speed of about 330 miles per hour. The Tigercat could exceed 430 miles per hour. This meant that any engagement occurred entirely on the American pilot's terms. Want to fight? The Tigercat could close at will. Want to disengage? The Zero couldn't possibly keep up. The speed advantage alone would have neutralized every tactical doctrine Japanese pilots had developed. The climb rate disparity was equally devastating. A Zero needed 7 to 8 minutes to reach 20,000 feet. The Tigercat could reach that altitude in under 5 minutes. Japanese pilots relied heavily on altitude advantage to control engagement geometry. Against Tigercats, they would never have altitude advantage. American pilots could climb above Japanese formations, dive through at speeds the Zero couldn't match, and climb back to altitude before the Japanese could respond. The firepower difference would have been the cruelest factor. Zero pilots were accustomed to American fighters carrying 650 caliber machine guns, formidable but survivable armament. The Tigercat mounted 450 caliber guns plus 4 20mm cannons. A single burst from this armament would literally tear a Zero apart. The Japanese aircraft's lack of protection meant that even a few rounds from a 50 caliber gun could cause catastrophic damage. 20mm high explosive rounds would obliterate Zeros in single hits. Patricia Donnelly spent considerable time analyzing what combat between Tigercats and Zeros would have looked like. She had access to gun camera footage from Pacific battles, engineering data on both aircraft, and pilot testimony from numerous encounters. Her conclusions were sobering. In any scenario she modeled, the Tigercat possessed such overwhelming advantages that the outcome was never in doubt. The only question was how quickly the Japanese pilot would die. A typical engagement would unfold like this. Japanese fighters on patrol at 15,000 feet spot an American formation below. Standard Zero tactics call for diving from altitude to attack, using speed from the dive to compensate for lack of raw power. Against Wildcats or even Hellcats, this worked reasonably well. Against Tigercats, the American pilots would simply accelerate away while climbing, reaching altitude above the Japanese before the Zeros could complete their attack. Now the Americans hold every advantage. They dive on the Japanese formation at speeds exceeding 450 miles per hour, faster than Zeros can achieve even in vertical dives. The Tigercat pilots select targets, close to gun range before the Japanese can react, and open fire with 8 guns simultaneously. A Zero hit by this combined firepower simply disintegrates. The 20mm rounds punch through the thin aluminum skin and explode inside the airframe. The 50 caliber rounds shred control surfaces and structural members. The unprotected pilot is killed instantly by fragments that would merely injure an American pilot protected by armor. The entire engagement from first shot to catastrophic destruction takes perhaps 2 seconds. The Tigercat pulls up using power and speed the Zero cannot match, climbs back to altitude, and selects another target. The surviving Japanese pilots attempt to turn inside the American aircraft, the one maneuver where the Zero holds theoretical advantage, but the Tigercats simply refuse to turn. They maintain speed, stay beyond Zero performance envelope, and attack from positions where Japanese pilots cannot respond. Within minutes, an entire Japanese formation is destroyed without the Tigercats suffering a single hit. This isn't combat, it's execution. Every advantage the Zero possessed is irrelevant. Maneuverability means nothing when you cannot force an engagement. Range means nothing when the enemy destroys you before you reach the target. Pilot skill means nothing when your aircraft cannot reach positions where that skill matters. William Schwendler ran similar simulations with Grumman's engineering staff. They modeled dozens of combat scenarios using actual performance data from both aircraft. In every case, the Tigercat dominated so completely that the exercises became repetitive. Change the altitude, change the tactical situation, change the number of aircraft involved, the outcome never varied. The F7F was simply too fast, too powerful, and too well armed for the Zero to contest. The night fighting capability would have been perhaps most devastating. Japanese naval aviation had virtually no night combat capability. Their fighters lacked radar, their pilots lacked instruments and training for night operations, and their doctrine emphasized daylight operations exclusively. The Tigercat's radar-equipped night fighter variant would have slaughtered Japanese bomber formations in darkness with complete impunity. Japanese bomber crews, accustomed to operating at night to avoid American fighters, would have found themselves illuminated on radar screens and destroyed by an enemy they never saw. No defense existed against radar-directed night fighters. Japanese aircraft lacked radar warning systems, chaff, or electronic countermeasures. A Tigercat pilot could track targets in total darkness, close to gun range using radar guidance, and destroy aircraft whose crews never knew they were being hunted. The psychological impact on Japanese pilots would have been catastrophic. Zeros had given Japanese naval aviators confidence bordering on invincibility in early war years. They knew their aircraft was superior to anything Americans fielded. They knew their training and experience exceeded American capabilities. Suddenly encountering an aircraft that negated every advantage would have shattered that confidence completely. How do you maintain morale when your best pilots and your best aircraft are being destroyed without landing a single hit? How do you convince young pilots to climb into Zeros knowing that Tigercats are hunting and their chances of survival are essentially zero? Commander Nakajima, struggling with training quality issues, later admitted in post-war interviews that pilot morale was fragile even without facing aircraft like the Tigercat. Student pilots heard stories from returning veterans about American numerical superiority and improving tactics. They understood that their odds of surviving their first combat tour were poor. If Tigercats had entered service in 1942, Nakajima believed that recruitment would have collapsed entirely. Nobody volunteers to fly missions that are certain suicide against an unbeatable enemy. The strategic implications extended beyond individual combat. Japanese naval aviation doctrine emphasized offensive carrier operations. The Pearl Harbor success had validated this approach. But carrier operations require maintaining combat air patrol over the fleet, defending against enemy strikes, and escorting your own bombers to targets. Tigercats would have made all three missions impossible. Japanese combat air patrol would have been swept aside by aircraft they couldn't intercept. Japanese carriers would have been defenseless against American strikes that Zeros couldn't prevent. Japanese bomber formations would have been massacred by escorts they couldn't evade or fight. Admiral Chuchi Nagumo, who commanded Japanese carriers through multiple battles, relied on Zero superiority to make his offensive operations viable. His doctrine assumed that Japanese fighters could establish air superiority over the battle space, allowing bombers to attack while defending their own carriers. Against Tigercats, this assumption would have been invalidated immediately. First combat encounter would have taught painful lessons about American technical superiority. But by then, Japanese carriers would have been vulnerable with their air groups destroyed and no capability to defend themselves. the industrial dimension made Japanese situation even more hopeless. Grumman's production capacity in 1943 exceeded 300 aircraft per month. The company had transitioned to assembly line production, with partially completed aircraft moving through stations where specialized workers installed specific components. Quality control was rigorous but production was rapid. If Tigercats had been ordered into mass production in 1942, Grumman could have delivered hundreds per month by mid-1943. Japan's aviation industry possessed no comparable capacity. Mitsubishi produced Zeros at perhaps one-tenth the rate Grumman could have produced Tigercats. Japanese manufacturing relied on skilled craftsmen building aircraft almost individually. The precision and quality were excellent but the volume was inadequate for attrition warfare. American production capacity meant that even if Japanese pilots somehow developed tactics to counter Tigercats, they would simply be overwhelmed by numbers before those tactics could make a difference. The material shortages worsened Japan's situation. By 1943, American submarines were strangling Japanese logistics. Raw materials that Japanese industry needed were stuck on ships sunk before reaching home ports. The aluminum, steel, and rare metals required for aircraft production became increasingly scarce. Even maintaining Zero production became difficult as strategic materials disappeared. Tigercat production would have suffered no such constraints. American industrial capacity and secure supply lines guaranteed unlimited access to necessary materials. Fuel shortages created another crisis for Japanese aviation. Training new pilots required fuel for flight hours. Operating existing forces required fuel for missions. As tankers were sunk and oil supplies dwindled, Japan faced impossible choices. Cut training and produce poorly qualified pilots, or cut operations and conserve forces. Either choice led to defeat. Meanwhile, American forces had unlimited fuel supplies. Tigercat pilots could train extensively, fly long missions, and operate without concern for conservation. The maintenance comparison was equally stark. Zeros required skilled mechanics and specific spare parts. As the war progressed and supply lines collapsed, maintaining Zero operational readiness became increasingly difficult. Aircraft sat grounded awaiting parts that never arrived. Mechanics improvised repairs with inadequate materials. Operational availability declined steadily. Tigercats, built to American standards with redundant systems and robust construction, required less maintenance and were easier to repair. When parts were needed, American logistics ensured rapid delivery. The operational availability of Tigercat units would have far exceeded Japanese fighter squadrons even with equivalent numbers. Consider a hypothetical carrier battle in mid-1943 if Tigercats had been available. A Japanese carrier force launches a strike of 40 bombers escorted by 30 Zeros. American radar detects the formation at 80 miles. A combat air patrol of 8 Tigercats is vectored to intercept. The Japanese formation is flying at 15,000 feet, standard altitude for such missions. The Tigercats climb rapidly to 25,000 feet, positioning above and ahead of the Japanese formation. At 10 miles range, the Tigercats dive through 450 miles per hour. The Zero escorts attempt to intercept but cannot reach the diving Americans. 8 Tigercats make firing passes through the Japanese formation, each engaging multiple targets with devastating firepower. Within 30 seconds, 12 bombers and 8 Zeros are destroyed or so badly damaged they cannot continue. The surviving Japanese aircraft break formation attempting to evade. The Tigercats, using superior speed, pursue individual targets and destroy them methodically. 20 minutes after first contact, the entire Japanese strike force has been annihilated. The 8 Tigercats return to their carrier without damage, ready for immediate relaunch. Meanwhile, an American strike force approaches the Japanese carriers. Japanese Combat Air Patrol consists of 16 Zeros maintaining station at various altitudes. The American strike includes 12 Tigercat escorts. The Japanese fighters detect the American formation and move to intercept. The Tigercat escorts engage, using superior speed to control engagement geometry. Within minutes, the Japanese combat air patrol is destroyed or scattered. American bombers proceed to their targets unmolested. Japanese carriers, now defenseless, are struck by multiple bomb and torpedo hits. The battle is decided not by pilot skill or tactical genius but by overwhelming technical superiority of aircraft the Japanese cannot match. This scenario isn't speculation or American propaganda. The performance characteristics are documented. The tactical outcomes follow logically from those capabilities. Japanese naval aviation would have been helpless against properly deployed Tigercats. The only question would have been how quickly the one-sided slaughter demoralized Japanese forces into complete defensive paralysis. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out.